Okay, so today we'll continue again with inner product spaces. Mainly, we'll discuss distances between. So there is a space given space W, subspace of a given vector space phi. Now there is another vector phi, and we need to find projection of this phi on W. This is our main topic of discussion. So let us solve the first problem. So here you can see R3 is equipped with standard inner product. So standard inner product means it is already known that x1, x2, x3 and another element y1, y2, y3. The inner product will be given by sum of those components, right? Because it is R3, if it is the space was C3 instead of R, then we take conjugation and just multiply the same thing. So since it is R3, just skip the conjugation part. It will not affect. Now here you can see W, the given space W is generated by those vectors, those kind of vectors. So you can see that is same as W is generated by this vector, right? 1, 1, minus 1. It is product of this. If you multiply it with x, you will get that desired element. So we need to find the projection on this space. That is the W here. In this case, W will look like this, and there is another vector. So what is that vector? It is beta. So beta is given as 10, 4, 5. We need to find this distance. Sorry. So this will W will look like this. Maybe write it as alpha. Let alpha equal to 1, 1, minus 1. So put it here. Now what? How can we compute distance between those two things? So just what can be done? We take the projection. So what is the projection? Let us denote the projection by E. So E of beta, this is the projection E beta. It is defined as E applied on beta. What is the formula for projection? It is simply take this inner product, divide by norms, and multiply with alpha. That is as usual. In general, in physics also, we already know, right? How do we compute those projections? Just taking dot product.
Sir, why multiply by alpha, sir?
Yes.
Why you multiply alpha, sir?
Why I am multiplying alpha?
Yes, sir. Because projection is a distance, na?
No. Projection is this part. E beta means this
distance.
vector.
This is distance, na?
No. Distance will be this, but projection is this part. Right. So this is our alpha. We are taking projection of this beta on this alpha.
Sir.
Yeah.
Sir, dot product is always a scalar quantity.
Yes, this is scalar, but if you multiply with alpha, then this will give a vector in this direction, right?
Yes, sir.
Okay.
Yes,
So
sir. That is what I am asking.
yeah. So that is, so you know the direction will be alpha, but you need to multiply with some scalar so that it gives you the projection.
Yes,
Right?
sir. Yes, sir. So projection is actually a vector itself.
Yes, projection is actually a vector. So how can you define a projection? So given a vector, so
Sir,
yeah.
in case of sir, in sir physics or say in geometry, sir, we sir when we talk about sir projection of a line segment,
Yes.
then we simply write it as AB cos theta, where theta is the angle between the two
Yes.
line
Yes.
segments. So, sir, that is, sir, scalar quantity, sir.
No,
That,
that is actually what you are talking. That is actually dot product, not projection.
yes, sir.
A times b cos theta. That is. So let me define projection. So it will be more convenient. So projection. Suppose W is the subspace. This is W. Here I have drawn two-dimensional subspace. It is generated by two vectors. Now, given another vector V, so W is a subspace of given vector space V. So what is the projection? Projection is a vector in W such that, so projection is a vector maybe denoted by some W0 such that for all W belongs to W, norm of V minus W0, this is less equal to norm of V minus any W. So it means projection is a vector in W which minimizes distance between those two vector space. So this is the distance between this W0 and V. So this distance is minimized by the projection. Okay, and you can explicitly describe the projection. So let me define here again. Projection of V on the subspace W is a vector W0 belongs to W which minimizes the distance, which minimizes the distance. So I have explicitly written what is the meaning of minimizing distance. So projection means it is some kind of approximation of this V, but in this subspace. Because you can easily see that V is not lying in W, but what can be done? So I am not. I am making something which gives minimum distance from V.
Yes, sir.
Okay, so you can see that this explicitly this W0, we can find this W0 explicitly, and this W0. So suppose W is generated by those kind of vectors alpha 1 up to alpha n. Okay, n dimensional. Yes. Then W0. Yeah.
Yes.
Okay.
Sir, for projection, we need some direction, na, sir?
Yes. I am explicitly mentioning. So W is a vector, right? So W has some direction. W0, sorry.
Sir, sir, is projection operator and this projection is different?
Previous projection operator that was actually not orthogonal. So in that case, I will discuss later. I will give an example which is a projection but not orthogonal projection.
Okay, sir.
Okay. So W0, it is simply take that given vector V. So projection of V on W, this can be defined as take projection of V on one direction. First, let us take the projection on alpha I direction. So it is given by this formula, and just take the sum of all those things. So I equal to 1 to n. So this will give you the projection of this theta on this subspace W. Okay, and this is actually called orthogonal projection. So yes, it is true that there can be other projections which are not orthogonal. For example, you can define something like this. So let so another thing is that this W0. Okay. So what can be done? For example, uh, just take this element x comma y in R2. Those are belongs to R2, and define something like this. pxy which sends okay. So I'll explain why this is not true. Actually, orthogonal projection has a property that orthogonal projection is always symmetric. It's not symmetric. It is what is called. It satisfies the property A star is it is self adjoint.
Sir, what is orthogonal projection? Sir, I think it is not described in.
So orthogonal projection, I have just written the definition of orthogonal projection. That is the definition of orthogonal projection.
Okay.
And you can check that this correspondence for V you get a W0. So this is actually a linear transformation because you can easily see that this formula what is the formula? It's sending V, right? It sends V to something like this. V comma alpha I by norm of alpha I squared into alpha I.
Yes, sir. This is linear.
This is linear because those are linear combination of those alpha I, and because there is V and you can use linearity property of inner product. So it is clear that
Yes, sir.
it is linear. So I will denote this orthogonal projection by E. Okay. So this is actually EV.
So, sir, projection of a vector simply means that we are talking about orthogonal projection.
Yeah.
So, for orthogonal projection, we have to write V as direct sum of W plus W complement.
Yes. So that is actually consequence of that part. So let me, since you have already told, so let me mention that thing. So you can see this is a projection. Now what can be done? You can also project these things on this. Maybe you can take the normal thing, right? So there is another thing you can define. Since V to I minus E. So maybe write it in this way. Send V to that I minus E of V. Then it is clear that is I minus what is I minus EV. This is actually I times V, which is V minus EV, and EV is same as this W0, right? So V minus EV, that will give you this normal part, this
Yes, sir.
vector. So there are two things, and you can now check that this and these two things are orthogonal to each other. That is, you can check that if you take inner product of those two things, that this will give you 0. So any vector uh, which is which can be obtained by I minus EV, those are in the orthogonal complement. Even you can write any vector V. So from here you can see that any vector V, this can be written as EV plus I minus EV. So EV belongs to this W, EV belongs to W, but I minus EV, this belongs to W part, right? W part mean you already know, right?
Yes, sir.
All those vector whose inner product with any element of W will give you 0. So let me mention what is W part. W part is all those vector V belongs to V such that inner product with W is 0. So you can see this I minus EV, that is inner product with EV will give you 0.
Yes, sir.
Okay. So that is a summary of orthogonal projection, and
So,
from here,
sir,
yeah.
sir, what is the quickest way to find, sir, projection of V?
What is the
So, what is the quickest way to find is an orthogonal projection of any vector space or
okay?
vectors?
Yeah, I'll tell you. So if from here you can see that every vector space can be written as W plus W bar because of this fact.
Yes, sir.
Okay, so you can check all those proofs. Those are actually given in Hoffman-Kunz's chapter.
Sir, W direct sum W perp is always V.
Yeah,
Yes, sir.
always given those are finite dimensional subspaces. Otherwise, there are some problems, some slight
This
issues.
is true for only for finite dimensional vector spaces.
Yes, that can be written for finite dimensional, and for infinite dimensional spaces, there is some small issues, some closeness or something. So I don't want to discuss those part actually. Okay,
No, sir.
is there any doubt?
No, sir. So, sir, we have to write the vector in form of W plus W perp, sir.
Yeah. So this element belongs to W, and
Hmm.
that other part is in W part.
Yes,
So
sir.
given any subspace W, you can define orthogonal projection on that W. That will give you one part. And now, since you already defined this orthogonal projection formula by this, now I minus EV, that will give you the component in W part.
Sir, we can define E in terms of, sir, we write, sir, if we have given, sir, direction, then we write the vector as the sum of the, sir, vector in W and in the direction of W, and
Yeah,
then, yes, sir.
you
And in
just
the,
project you just take projection of V individually on in each direction alpha 1 up to alpha n, and just take the sum.
yes, sir.
So it is, those story are similar to something like direction cosines. Those are you are familiar in.
Yes, sir. Yes, sir.
Yes, that is similar to that part.
Yes, sir.
Okay, so back to our problem. Here you can see that so we need to find this. First we need to find E beta, then this is same as beta minus E beta, right? As we have already discussed, we need to compute this distance. So we need to compute norm of this part. Okay. So let us find E beta first. So I just copy this part E beta. Okay. E beta is same as, what is the inner product with beta and alpha? So it is
Beta and alpha
1 into 10 plus 1 into 4
minus 5.
minus 1 into 5, and norm alpha squared. It means 1 square plus 1 square plus minus 1 square into alpha, right? But this is same as uh, 9
9
by
alpha by under root
that is 3 alpha.
3 alpha.
So now 3 alpha means, let us explicitly write 3 alpha means it is actually 3 minus 3, that is alpha. So therefore beta minus E beta, this is actually, what is the value of beta? 10 4 5 minus 3 3 minus 3, so which is same as 7 6 plus 8, right? 7 this is 4 minus 3, which is 1. Okay,
Sir,
yeah. Therefore norm of beta minus E beta, this is actually square root of inner product, right? Which is 7 square plus 1 square plus 8 square, which is same as square root of 114, right? So option P is the correct answer. Okay. So yes,
sir, so computing, sir, the projection of beta simply means that we are finding the projection on W along W per.
yeah,
Yes.
exactly. Okay.
So, sir, we can also find this is like we have given the basis of W, and if we find the basis of W per and write the vector sir alpha in terms of the basis of sir
W per, yes.
yes W per and W, then we can also in this way find the sir
Yes, we can
projection.
find projection. Yes, right. Okay. So let us see the next question here. E is given as this formula. So orthogonal projection is already given. This is inner product space, and orthogonal projection of V on W is given by this formula. Now we need to find W per. Okay. So what is W per?
I minus E.
Hmm?
I minus E V sir.
Yeah.
But we are not given W.
Yes. W is not given, but we know what is the projection. So this is our space, given space, and any vector V will fall on this part, right? EV. So the space W, it will be generated by those kind of vectors, because is it clear? W can be written as EV for all V belongs to V, because you need to see
Yes sir.
within
E,
perspective.
sir, EV is simply W.
Yeah, exactly. EV is actually simply W, because E acting on W is W, right? Because V, as we have already seen, V can be written as W direct sum W per. Now, if you apply E, that second component will goes to 0, but the first component will go to EW, and EW means projection of any element of W in W, means it will give you the same thing, right? EW is W.
Yes sir. Sir, option A.
Okay, so let us see. So W is actually this range space, because projection
Yes.
will
Yes.
lie on the space W itself. So
Yes
W
sir.
equal to EV. Okay, so let us see what is the orthogonal complement, right? So orthogonal complement W par, it is simply all those vectors of this form, right? Those are I minus EV, orthogonal complement of.
Yes.
Is it clear? Because
Yes sir.
orthogonal complement is unique, and all those kind of vector will give you the orthogonal complement.
Yes sir.
So the W part, it is same as I minus E applied on V for all V belongs to V. It comes from the previous discussion. Just discuss now. Now, uh, okay. Instead of doing this, we can. Uh, so what do we need to do? We need to find W part. Yes. So W part can be written as I minus E acting on phi, such that phi belongs to phi. But V will look like this XYZ, right? XYZ. So I minus E acting on XYZ, by definition, this is actually same. So let us calculate this first. This is same as XYZ minus X plus Y by 2, comma X plus Y by 2, comma Z, by this definition. So subtracting this will give us x minus y by 2, y minus x by 2 and 0. So this is the correct answer. So W perf will be given by those kind of vectors. So W perf can be written as all this such that xyz belongs to
Sir,
yeah.
orthogonal projection of V on W per is simply W per.
Orthogonal projection of V on W perf is simply W perf. Yes.
Yes, sir. Yes.
Yeah.
Sir, we can also find this we have, sir, W,
Yeah.
and so we will have basis of W, and so here we see that basis of W, dimension of basis of W is 2. So we need one vector in W. So there will be one vector in W per, sir.
Exactly. You can do in
We
that
if
way also.
we are able to find any vector which is perpendicular to both the basis vector, then it will form W per.
Yeah. That
And
will
then
form
we
W.
we sir we generate the sir W per by that vector. So
Yeah.
yes, sir.
W perf will be generated by that vector.
Yes, sir.
Oh, sorry. Actually, I have computed orthogonal that space W perf, but in this question we need to find orthogonal projection on W perf, right? So
That
first,
is W per na, sir.
yeah, that will be actually that can be obtained from this answer actually I minus e. So that question is slightly different. So we need to compute this part actually I minus e acting on x y z.
Yes, sir. Yes, sir.
Answer is okay, but because on W part the projection is given by this I minus e. This
Sir, how can we, sir, find W per by this by the method I was discussing, sir?
okay. So you if you know he can be written as W plus W part, then you have already obtained, right? Any V can be
Yes,
written as W plus W means this is equivalent to say V can be written as some W plus W dash. Where W belongs to this
yes, sir.
and
Yes, sir.
W dash. So you
Correct.
just take that W or that W dash wherever you are projecting.
Yes, sir. You are right.
Okay. Okay. So this is our aim actually. This is aim XYZ. That is projection on orthogonal complement. That is given by this I minus E of V. Okay. Now let us see question number 3. Here, what is given? Again, orthogonal projection E on a subspace W, it is given by this formula. Standard unit product space, otherwise those answer will be different. Okay. Now, uh, the question is the subspace W is. So we need to find this subspace where the projection is done, right? So again, the subspace W, it is actually EV.
Yes, sir.
That is, subspace can be written as all those things such that XYZ belongs to phi.
Range space of E.
Is it clear?
Yes, sir.
But we need a different expression. That is, we need to see from this equation. It is clear that we need to find all those elements
Which are in null space. Some.
which are perpendicular to W part. So what is W part? We know V can be written as W plus W part, right? So an element of W is given by, so W can be again, W is same as W part of part, right?
Yes, sir.
So if you identify W part, then W can also be written as all V belongs to V such that inner product of V with element of W perp. So let me denote it by W dash equal to 0, where W dash for all W dash belongs to W perp. Is it clear that another expression of this W is same as W perp of perp?
Yes, sir.
Because this uniqueness of this decomposition. So W perp it will give you the same W.
Sir, in this notation, the subspace W written as in this notation, this simply means that W is a null space of some projects, some operators. Sir.
Yes, this can be thought because yeah. So if, for example, projection takes all those elements from W perp goes to this 0, right? Sorry, if some element is from W perp, so let me write two-dimensional scenario. So those are x-axis and this is y-axis. So projection on x-axis means anything in the direction of y-axis will goes to 0.
Yes, sir.
So actually projection can be thought as kernel of this projection operator. Sorry, null space can be thought as orthogonal complement can be
I
thought as
minus E, I minus EV, null
I
space
minus
of I minus. Yes.
no null space of E. Orthogonal complement, this is the orthogonal complement, this direction, and it is actually null space of this operator, because what you are doing, you are projecting this thing to this. So if something is in the direction of y, that goes to 0.
Yes, sir. So null space of the in W.
Yeah, so null space of E, null space of E, that is
Orthogonal
actually W.
projection. Yes.
Okay. So let us first find W part first. So W part can be given by this formula, right? So our answer W part can be written as I minus EV, such that V belongs to V. We have already seen. Now what is I minus E? I means identity operator. So in our case, what is I minus E XYZ? This is simply XYZ minus this part. So XYZ minus 5x minus 2y minus z by 6, comma, minus x plus y plus z by minus z by z by 3, sorry, comma, minus x minus 2y plus 5z by 6. So if you subtract, what will you get? It is same as x minus, so x becomes 6x minus 5x, which is x plus 2y plus z by 6, comma, 3y minus y, that is 2y, and x plus 2y plus z.
So there will be 8y, sir, in first coordinate, sir.
Yes,
There is 8y, sir.
no, it is 6z, 6z minus z. Sorry, 6x minus, there is only single z, right?
Okay, sir. Correct. Correct, sir.
Okay, so 6z minus 5z means again z, and there is x plus 2y. So now you can see that W per can be any element of W perp. It will look like x plus y plus z by 6 times this element, right? Uh, 1, 2, 1. So W perp is actually generated by this 1 to 1 single element. Okay. Now W perp is 1 to 1. Then what is W? W is also such element which are perpendicular to this W perp. That is, W is same as W perp, which is same as all phi such that phi perpendicular to this 1 to 1. Maybe write it as xyz such that xyz is perpendicular to 1 to 1.
Sir, there should be 2i, sir.
Is there any mistake? 1,
Yes.
2.
X plus 2i plus z by 6 times 1 to 1. Left
Is
side.
okay, right?
X plus 2i plus z.
X plus 2y plus z. Yes. So this is orthogonal, means this equal to 0. So it is same as saying,
Sir, where you calculated I minus e, sir.
yeah.
So, sir, last equality, sir.
Last equality, there any mistake?
Yes, sir. There should be x plus 2i plus z by 6 times 1 to 1. 1 comma 2 comma 1.
Yes, those are 1 to 1.
Sir, in left side, sir. In left side. Sir, x plus 2i plus z, sir, the scalar quantity, sir.
Oh, sorry. X plus 2y plus z by 6.
Yes, sir.
Okay. That will not create any problem because those are actually scalar, and any scalar can be written in this form. In
But,
particular,
sir, we cannot give the same answer, sir.
we are computing this W actually. We are computing W part.
Yes, sir.
And
That is, sir, fine, sir. But the steps we have followed, we should have written x plus 2y plus z by 6.
yeah, that is okay. So is it okay now?
Yes, sir.
X plus 2y plus z equal to 0. So that should be the correct equation.
Sir,
Option A.
also we can try to find the null space of I minus e.
Yes, you can find null space of I minus c. That way, actually we have done that thing actually. So we have taken I minus c, and we are trying to see all xyz such that I minus e of xyz equal to 0. So which is same as x plus 2y plus z equal to 0. Is it okay? So we are actually trying to find null space of I minus c.
Yes, sir.
So that again, if you equate 0 here, that
This
will give you
1 comma 2 comma 1 cannot be 0, so that quantity.
yes.
So now it will create a difference, sir. You are saying that we can write anything, sir. Any.
Yeah. Now that will create a difference, right?
Yes.
Okay, thanks. So you can compute in that way also, because we have seen that W perf is null space of E. W perf is null space of E. By the same reason, W is null space of I minus E. Okay. From here also you will get the same exact result, and maybe that way is easier because in some cases uh, W perf maybe W perf can be generated by more than one element.
Sir, if, sir, any vector space, vector subspace is given in this form, sir, W is equal to some equation and equal to 0,
Yes.
then can we find, sir, the basis of that vector space explicitly, sir?
Given by this equation.
Yes, sir.
Okay, those kind of thing can be obtained by doing those kind of operation, right? Row operation.
So we simply put the value of sir x, replace the value of x or any variable sir in x y z.
Yes. For here it is easy. If there is only single equation, you just put z equal to minus x minus
Yes,
2y,
yes, yes.
and you write it as generated by those two elements.
Mm.
For example, here it is minus x minus 2y means z equal to minus x minus 2y. That means here z equal to minus x minus 2y. So you can write it as x times 1 0 minus 1 plus y times uh, 0 1 minus 2. But otherwise, in general, you solve those kind of equation, right? You need to find kernel of that
Yes,
system.
sir. Fine, sir.
Oh, okay, so let us see the next question here. Uh, W is spanned by the vector 2 comma 3, and again E is orthogonal projection of R2 onto the surface W. Standard inner product is considered. Now there are two vector E1 E2. Then which of the statement is correct? So uh, we need to take projection onto this subspace generated by 2 comma 3. So let us see what is happening here. X1 comma x2 is a given vector v, and we need to project it onto this alpha. Okay, this is the direction alpha. Alpha is actually 2 comma 3. So again, the projection is given by this formula, right? Projection if he, this is actually same as mm, sorry,
Summation
3 comma alpha. There is no
alpha
other
is
element, so it is simply
normal.
okay. So what is v inner product v comma alpha? This is simply 2x1 plus 3x2, right? What is norm alpha square? This is 2 square plus 3 square. This is alpha, and this is, so it is given by 2x1 plus 3x2 by 13 into 2 comma 3. So we need to see which are incorrect. So this this is matching with this answer. So this is correct. So this option is correct. Now we need to see uh, what is E with respect to the standard basis. So from here you can see E applied on 1 comma 0. So let me write E applied on the first E1 1 comma 0, that will give us 2 by 13 uh, into 2 comma 3, right? So it is same as 4 by 13 E1 plus 6 by 13 E2. Similarly, E applied on E2, which is 0 comma 1, this will give us 3 by 13 2 comma 3, which is same as 6 by 13 E1 plus 9 by 13 E2. Therefore, matrix representation of this E with respect to this given basis generated by E1 E2, this is same as what is the process? We just put those
4 by 3,
yeah
6 by 3 in column wise.
yes. So this is our the first
2 by
column.
3, 9 by 3, sir.
This column this
6 by 3, 9 by 3 in column, sir.
3, 6 by 13, 9 by 3. Yes.
The second option B is correct.
Second option is also correct. So we need to find incorrect option. Now the component of x1, x2 in W part. So again, x1, x2 in W part means it is given by this formula, right? I minus E of this vector V. This is EV and this is I minus E. So the component on W part, this is actually I minus E applied on V. Now what is V? What is the formula? EV, EV is given by this formula, right? So component of V on W part. Now here V is actually XYZ. V is given as x1 and x2. Okay. V equal to x1, x2. So first, what is IV? IV means it is x1, x2. Identity operation on x1, x2 minus EV. What is EV? EV is given by 2x1 plus 3x2 by 13 into 2 comma 3. So let us multiply here. So it is 2 times this 4 6 plus comma 6x1 plus 9x2 by 13. Right? I have just taken written this explicitly. So now if we subtract, we will get 13 minus 4, which is 9x1 minus 3x2 by 13. Sorry, 9x1 minus 6x.
By 13. Second component is, sir, 4x2 minus 6x1 by 13.
Yeah. What is what you said? 4x2. Yes.
4x2 minus 6x1.
Minus 6x1 by 13. So this is also matching, right? 4x2 minus 6x1 by 13 minus 9x1 plus 6x2 by...
No, no, sir. No, no. Sir,
Oh, minus
9x1 is
9x.
positive.
So there is a sign issue here.
So last one is matching, sir, but C is not matching. So this option will be correct.
Yes. So this is incorrect. Therefore, this will be the right choice. We need to find incorrect option. So let us see this last, and this is also correct. This last option is already correct. There is no sign issue. Okay. So let us see question number 5. Okay. Here V is finite dimensional inner product space, and the basis is given by n element alpha 1 up to alpha n. Those are orthonormal basis. So again, orthonormal basis means alpha I inner product with alpha j, that is 1 when I and j both are same, and it is 0 when I and j are not same. So that is definition of orthonormal basis. Now we need to find, so let T be linear operator on V and A be the matrix representation of T with respect to this basis. So we need to see how can we write the matrix in terms of inner product. So okay, so let A, which is same as ARS, this matrix be the matrix representation. Matrix representation. So now you know that any element phi, this can be written as, you already know, right? So let us write phi can be written as sum of Ci alpha I.
Yes,
Now
sir.
taking inner product with alpha j, that will give you sum of
Yeah.
Ci alpha I alpha j.
Only we get Cj.
Yes, so we only get Cj. Therefore, any element phi, therefore phi can be written as sum of,
Summation inner product V alpha
yeah,
I then from 1 to n,
yes.
and alpha I.
So Ci Cj is, so let me write as j equal to 1 to n Cj alpha j. So Cj means
Inner product V alpha j.
phi alpha, sorry, phi alpha j, and now there is alpha. So it is similar to, now you can see that you can reinterpret this another way, that is, we take projection on all those components. So what, how can you write an element xyz? You just write it as sum of those components, right? Sum of the components on x direction, y direction, z direction. Now you are doing the same thing. So it is x direction, those component is x00, y direction 0y0, z direction 000.
Sir, if it was an orthogonal basis, then we would have divided norm alpha j
Yeah,
by.
since it is orthogonal, that's why alpha I times alpha I will, alpha j times alpha j will give you the same thing.
Yes, sir.
Okay. So V can be written as this. Now let us apply T on V. So if we apply T on V,
Sir, by linearity, it will be only act on alpha j, sir.
yeah. So it is same as phi alpha j, j equal to 1 to n, and T will be only acted on this alpha j, right? So this is how T phi will look like. Okay, all right. Now it is given, what is given actually. Okay. So T phi will look like this, but we need to find uh,
ARS.
again TV. We need to write TV as linear combination of those alphas, right?
Yes, yes.
So again by this formula, again by star, this can be written as, for example, T alpha j. Uh, sorry.
Sir, T alpha j, how can we find T alpha j?
Yes.
T
So
alpha j in terms of sir alpha
we
I.
need to write TV in terms of those. Maybe instead of writing TV, we can start with easier thing. Instead of TV, dif- let us write T alpha. Okay. So
Yes, sir. For matrix representation, we need the image of basis elements.
yes, it is enough to start with image of basis element to write matrix representation.
Yes.
So yeah. So T alpha I can be written as something like some combination of uh, maybe T alpha we can write it as some combination of this AJI alpha j. So that AJI coefficient will give us the correct matrix representation, right? Now what is this AJI? By star, we already know this. Just replace this V by T alpha I. So if we replace this V by T alpha I, from star we have T alpha I alpha j times alpha j. Is it clear?
Sir, TL5, yes, sir, clear.
This is Y star. So we have assumed this ARS or maybe AIJ. I am comfortable with this notation. So if AIJ is matrix representation, that means we can write T alpha 1. This is as, so those are actually example. T alpha 1, that is same as A11 alpha 1 plus A21 alpha 2 up to AN1. Similarly, T alpha 2 can be written as A 12 alpha 2, sorry, A12 alpha 1 plus A22 alpha 2 plus A32, like this. Is it clear?
Yes, sir. Sir, why we cannot write directly TL5, sir?
Why cannot we directly write?
T of alpha. Why we need, sir, V? First we define V, then we are writing, sir, this.
Yes, we can just start with this step actually. T of
Yes.
alpha I, this can be written as this.
Sir, how, sir?
Okay, so I have started with something wrong, not wrong, but the same technique will be used here. So replace this V by T alpha I, then we get T alpha I is same as this. But we also know T alpha I from the matrix representation, T alpha I can be written as this. This is by matrix representation, and T alpha I can be written as this. This can be written as this by star. Now if we comparing what we have, we have AJI is same as T alpha I comma alpha j. So that is the indices exchange, right? First, so that is same as ARS. If we put ARS, the first component will becomes sorry, is it okay? T of alpha I? Yeah, it is okay. Oh, so it is T alpha S comma alpha. So the indices actually switches, right? So this should be the correct option. T alpha is alpha A. Is it clear?
Yes, sir.
Because in matrix representation we do not actually put those in rows. We just put those things in column.
Yes,
We
sir.
take the transpose of that thing. Uh, that's why the indices are in opposite way.
Yes, sir. Sir, my question was why we cannot simply start by T alpha, sir?
Yes, you
Why
can
we need
start
to
with
start?
T alpha I. Actually, I have started with something different. It is
So,
better
sir,
to start
but
with.
how can we write T alpha? Sir, first we write alpha as, sir, summation of, sir, alpha j, like we proceed. We have done in, sir, previous, sir, one.
Yes. You just
But,
start with T alpha I, and T alpha I can be written as this. Again, by the same technique, we get this is T alpha I, alpha j times alpha j.
Okay, sir.
That's why I have started with V. Now you can replace this V by any vector. Since T alpha is also in V, we just replaced here. Any vector can be written as this. In particular, T alpha I also can be written as this.
Yes, sir.
So that's why those steps are actually not needed. It is already, you can already assume this step.
Yes, sir. T alpha is actually in V, so it
Yeah.
can be written a linear combination of alpha is, and so
Yes.
we get this.
Yes. Exactly. So you can directly start with this step, and you just you can remember this thing as is like this. You can remember this as uh, any vector can be written written as sum of the projection on each direction. So I am taking projection of this V on in the direction alpha j, and now I am taking the sum because those alpha j's are in those alpha j's are orthonormal, so norm is 1. That's why I have not written norm. Is it okay?
Sir, sir, we divide by norm or norm alpha square.
Not alpha just square. Norm alpha just square. Yes.
Yes, sir. Clear.
Okay. So let us see next question. Here, the inner product is not usual. It is slightly different inner. There are some coefficients. So with this inner product, what do we need to do? F is given as this equation, then the element beta, uh, or then the element beta. We need to find this beta such that F alpha can be written as alpha inner product with beta. So let me state some facts. So given an inner product space V with inner product V, there is an inner product. Now any functional. So suppose F belongs to V star, means F is a linear functional, right? So it means that is F is a function from V to the given field.
Correct.
Linear map,
Linear function. Yes, sir.
linear transformation, right? Now those kind of transformation, so F of V, this can be always written as V times some W for some fixed W. Okay,
Yes, sir.
so that says, that actually says any linear functional for a inner product, given inner product space, any linear functional can be thought as some projection. Your projects not exactly projection, because that element is in F.
Sir, beta is fixed always.
Yes, there exists some W for which FV can be written as V inner product with W.
Yes, sir.
Okay, this is for all any.
Sir, actually, we are projecting in one-dimensional vector subspace.
Yes, not one dimensional, because this is
Because
actually,
of beta is sir fixed, na, where the subspace is generated by beta, sir, we can think it as.
yes, it is similar kind of thing, projection, but we are not. We are just ignoring those direction, because usually what we write V comma W, if we take projection along projection onto this W space
Sir,
P comma W into W, but we are ignoring this W actually.
sir, what inner product of x comma y, sir, denotes?
What inner product of x comma y denotes?
Yes.
It it does not means, uh, and a better explanation will be so in vector means in physics those vector there is a notion of dot product, right? V dot W given to vector v1 and v2 we can multiply by this dot product. Now we are generalizing that thing in arbitrary vector space. It is not only limited on R3.
Yes, sir.
So now any vector space we can we can deduce the similar property. We can start with those similar kind of property, that is linearity, homogeneity, and positivity, those kind of property, and now we can derive all the other properties, and this is actually helpful because now we can do similar kind of lots of different um, application. For example, projection, that is approximation by some subspace, those actually make sense using this setup,
Yes, sir.
and so that's why this is helpful. And also you have already seen those kind of Cauchy square inequality, Bessel's inequality.
Yes, sir.
So without using any other tools, you can directly see those inequalities. Otherwise, those inequality is not easy to understand why this should be happening. Right? Those are
Yes,
some
sir.
abstract equation. But now it is clear that is norm inner product mod of inner product is always bounded by norm. Yes. So we are getting some kind of motivation that is
Yes,
similar
sir.
to v dot w cos theta is less equal to norm v norm w. So that is a more general thing which will be true in any inner products, and we can deduce lots of different inequalities. We can do lots of different things. We can play with those things, and we can find that any vector can be written as that is we have a decomposition which we do not have such kind of decomposition, but in general here we can see that if we project onto the orthogonal complement we have such kind of different decomposite position.
Yes, sir.
So that's why it is important to consider inner product. And so this is actually this lemma may be something. This lemma may be called Sur lemma or something. I have forgotten the name, but you can look at this, and it is actually easy to prove that.
Sir. Yes,
Yeah.
sir. Yes, sir. Yes. So this is a theorem, sir. Sir,
Yes.
I have proved it, sir.
This is theorem. This is a theorem, and there is some name to this theorem. Okay. So
Option C is correct.
okay. So let us try this. So f alpha can be written as alpha inner product with beta. Now, so what is alpha? F alpha is same as alpha inner product with beta. So
Sir,
let
x plus 4y plus 2z can be written as inner product xyz with 142.
yeah, you are absolutely right. So let
So,
us explicitly write. So given alpha is xyz, let alpha is xyz and beta is fixed element ABC. So alpha inner product with beta will give us x plus by plus cz. But it is also given that given f of alpha, it is given as x plus 4y plus 2z. Therefore, comparing coefficient, that is side note. Comparing coefficient, we have a equal to 1, b equal to 4, c equal to 2. So that is the correct answer, right? 1/4. Oh, no. That inner product is actually different. Just note here the inner product, it is slightly different.
Yes, sir. Yes, sir. Yes. Yes, sir. This
3,
is true only in case of standard inner product.
yeah, that's why. So just be careful here.
Yes.
3ax plus 2by plus cz. But this is same as x plus 4y plus 2z. So comparing coefficient, we have 3a equal to 1, 2b equal to 4, c equal to 2. That is a equal to 1/3, b equal to 2. 1/3, 2 and 2. So a is the correct option.
Sir,
Yeah.
3ax plus how you are written here?
So I am comparing those coefficients. We get 3a equal to 1 times x. So 3a will be same as 1, 2b will be same as 4, and c will be same as 2.
Sir, we can take multiple also, na, sir?
Yes.
Sir, we can take multiples also, na, sir?
So
This will be, sir, unique, sir. W will be unique.
yes, this beta will be unique.
Sorry, sir, beta. Okay, sir.
Yes, this w or this beta is unique. You can also check here that this must be unique, because if you choose another w dash, so suppose there is another w dash, then v comma w dash will be also same for all v. So those two are same. That means v comma w minus
W
w
is
dash.
equal to W dash, yes, sir.
Now put v equal to w minus w dash. That will give you norm of w minus w dash is 0, right?
Yes.
So we get norm of w minus w dash equal to 0, but that will imply w equal to w dash. Norm is 0 if and only if that is itself 0. That means those two are same. Okay. So I should write there exists unique w. That is the symbol for existence, and that that exclamatory symbol that says unique. So there exists unique w. Okay. So question number 7. Here, uh, matrix representation of T. T is a map from C2 to C2. That is a linear transformation with respect to standard order basis. Okay. So this is now we need to find T star. So let us first see what is adjoint. Okay. Adjoint operator. This T star is actually called adjoint operator. So suppose T be a given operator, then we have seen that Tx comma y, this inner product. So if you now vary all those y's and fix this x, then you can thought this tx comma y, this is another this can be thought as linear functional, right? So let me denote it by f of y, or phi is the correct name. So denote this phi y, this linear functional phi is a map from the given vector space to C, the field f. So you can write phi f as tx comma y. So this is actually sorry, this is not a linear functional. There is a slight issue, because c times y, there is some bar. some conjugate will appear.
Why, sir? In first coordinate, there is no, sir.
No. If you choose cy, phi of cy, then you cannot take c out, right?
Yes, sir,
There
yes,
will
sir.
be some cy. So that is not a linear functional. But what can you do? You just reverse the thing. Y comma tx. So fix x and vary y. So this will give you a linear functional, and by the previous observation we know those kind of linear functional, this phi can be always written as y times, oh, sorry, okay. So so we started with this tx comma y. Now, okay, so sorry, we can see this in this way also. Phi x can be written as tx comma y. So this is a linear functional of x. So fix y. Now this is a linear functional. Is it clear that if you just take another, if you just take x1 plus x2, you will get tx1y plus tx2y. So phi of x1 plus x2 is same as,
Yes, sir, yes, sir.
so those linear functional, it is clear. Now what can be done?
But this
Right?
is the property of a joint operator, no, sir?
Exactly. So you can write this as y times by previous, sorry, by previous things, any f of v, any linear functional can be written as inner product of v with w. So it can be written as x comma some w. W belongs to v. So for every y, we are associating something w, right? And the interesting thing is that this association is itself a linear transformation. So that's why we will write a linear transformation t star y.
Sir, what is actually T star?
Yes, that unique thing that for every y, so by previous observation, for every y there exists unique w such that phi x can be written as x comma w, right?
Yes, sir.
So we'll define this y to this w. This definition is called t star. And the interesting thing is that this is another linear operator.
Yes, sir.
So we'll use this notation actually. T star w, T star y. For every y, we have something. T star y. Okay. So this T star is actually called this T star is called adjoint operator. Adjoint operator corresponding to P. Adjoint operator of P. Okay.
Sir, why we do not take T star at some other vectors? T star W, sir.
Why?
T star W, sir. Why we do not write T star W? Why we are taking Y, sir? It simply says
No.
that T star Y is Y, sir.
Yes, I have already said that any linear functional can be written as x comma some w, right?
Yes, sir.
So that's why for every fixed y, I am getting some w.
Yes, sir.
So I am saying that for every fixed y, that w, this is a linear operator. This is another linear function, linear operator, linear transformation. And
Yes, sir.
what is the notation for linear transformation? This is denoted by some t dash. So I am denoting it by t star. So this w can be written as t star of this y. That's why I have replaced this w by t star y.
Okay.
So that's why t star is this. This is called, sorry. This is actually called adjoint operator. Okay. Now we need to find this t star xy. And another interesting property is that matrix representation of this t star. So if matrix representation of t, if matrix representation of t with respect to a basis is A, then matrix representation of this t star with respect to that given basis, it will be actually S star. S star means conjugate transpose. You can explicitly check that. That is very easy to check actually.
Yes, sir.
Okay.
So we need to find sir conjugate transpose of A. Then after that we need to find the linear transformation.
Exactly. So given A is, back to the our problem. So given A is I1 1I. I1 1I. So it is symmetric. So transposing will give you the same thing, but taking conjugate, sign of I will be negative. So 1 minus. So this is our conjugate transpose, that is S star. So now if we apply this, this is actually S star. If we apply this S star on xy, we have minus ix. What is the multiplication? Minus ix plus y, x minus iy, right? So we need to write it in the given form, that is t star applied on xy is same as first component is minus ix plus y, x minus iy. So second component is x minus iy. Those two are matching. But if we take I common, minus I common, this is the correct answer. Is it okay? Okay. You can check this part actually. Y conjugate matrix representation of this part you can check. It is not easy. It is actually easy to see. Even we can write this because uh, yeah.
Sir, this method is only true na in case of the if the
Yeah,
matrix representation is with respect to standard
orthonormal,
basis.
orthonormal basis. It will work for orthonormal.
Yes.
Otherwise, not. It will not work
So
because
it's given with respect to orthogonal basis, sir, right?
yes, yes,
So you have not mentioned anywhere,
yes.
right?
That's I should mention that part actually. Otherwise, this method will fail.
Sir,
Whereas if there is inner
yes,
product, we need some extra properties to deduce all those things. Okay.
sir, I have a question.
Yeah.
If we have given sir a linear operator, sir,
Yes.
sir, then how can we find T star? Is this process we need to, sir, again repeat, sir? I mean, sir, first we find, sir, matrix representation of T, then find this transpose conjugate, and after that, then we find T, sir, T star. Sorry.
Actually, we don't need those things. So
Then,
let me write the let me try with your method. So you have suppose we don't know about this that this is not known. Then we need to find T star of xy, right? So we have seen that. Just a minute. Okay. So what? How can we find those kind of thing? So we know that T star xy, maybe write it as T star v. T star v comma w. This is given. Mm, so you can write this as okay. So you can write this as AB is same as T v comma T sorry w comma T star v bar. Okay, so W can be written as T star phi, but as usual, this is same as T phi comma W. Sorry, T W comma phi. So we actually don't need those things, maybe because we know that any element, so T star W, any element will look like what is that? We already we have seen that fact. If given orthonormal basis alpha 1, so beta, suppose beta is same as alpha 1 up to alpha n, then T star W can be written as T star W comma alpha I sum of alpha I. Right? Now, if you take this property TW comma V, from here we can write this as, sorry, there is a conjugation, W comma T alpha I, sorry, T alpha I comma W. What is this? T acting on the second thing, comma W. Now, can you see that without using those that fact, we can directly write maybe a better notation, better way to write this as W comma T alpha I, this inner product with alpha. If you switch those two things, there is a conjugation, because we know alpha beta is same as bar of beta alpha.
yes, sir.
And that
Sir,
proves,
but the question remains to find W, sir.
question remains to find, no, I am
W.
applying T star on W, T star on this x comma y.
Yes, sir. Yes, sir. Okay, okay. W
Right?
is any element.
Yes. Alpha 1 up to alpha n is also given. 1, 0, that is given orthonormal
So
basis.
if we are given T, then we can find
Yeah.
the T star by this method, this procedure.
So
Yes.
though T star is explicitly written here, T star is defined implicitly as this, so it is not explicitly written, but we can deduce by this given orthonormal basis, we can always deduce.
Yes, sir.
Okay, this is explicit characterization of this T star. Okay, even the proof, whatever I was telling, that actually comes from this fact. You can easily look at why, because TW, you can write TW as same as T alpha comma, sorry, TW can be written as TW comma alpha I, their sum comma alpha I. But here you are writing W comma T alpha I.
Yes, sir.
So that's why those conjugation that IJ's indices actually switches. You can explicitly try this. Previously, we have already written what is those AIJs, and if you again find AIJs from here, you can look at those IJs will get switched, and there is a conjugation because of exchanging of those places. Okay, so that's why conjugation transpose will appear. T star is same as A bar transpose. So the proof is already given in that book. You can look at that. It is easy. So next question here, the linear transformation is given by this formula. Linear operator is given by this formula. R3 is vector space over R. Standard inner product is considered. What is the adjoint operator? T star 1 5 minus 2. So again we already know the formula, so we'll use that formula. So
Sir, if we change the basis, then the operator will be different, na, sir?
yeah, if you change the basis, there will be no issue because 1 5 minus 2, that is also written with respect to that basis. Whatever
But we have
basis,
not mentioned the, sir, basis here.
yeah.
We take standard basis.
Even if you choose different basis, you will get the same answer.
Yes, sir. Let's see, sir, for these examples.
Yes. We'll choose the most easiest basis for our purpose. Okay. It may not be always the standard basis, may not be the easiest thing to work with. Wherever the easiest thing appears, we.
Yes, sir. But in this case, I think standard basis is
Yeah.
yes.
In this case, standard basis will be used. So we can see that T of 100, this is same as 2, 4, 5. E2 is same as 3 minus 1, 2.
2,
E3 means 001. So
3 minus 1.
3 minus 1. Yes. So we'll T with respect to the standard basis. This is the transpose of those things. Right? Sorry. T with respect to standard basis, we'll put those things in column. That is usual matrix representation.
Yes, sir.
Therefore, T star, we have already know that T star with respect to the same basis, this will be given by. So let,
Column wise 2, 3, 1.
yes, A bar transpose. So there is no meaning of bar here. We just simply write the transpose. 2, 3, 1, 4 minus 1, 3, 5, 2 minus 1. So now if we apply A bar transpose on 1 5 minus 2, this, so note that 1 5 minus 2, we are not applying these on 1 5 minus 2, though those are looking same because of our choice of standard basis, but actually we are applying the transformation, this matrix on its coordinate.
Coordinate triple. Yes, sir.
Yes. So that's why that will give the answer to your question, independent of choice of basis. So
So, but in that case, we have to multiply by that, sir. We only take. Yes.
yes. So even if you choose different thing, you will get different choice of basis. You will get the same answer. Okay. Though the representation will be different, but because whatever the answer you will get, you need to again.
We need to multiply by that coordinate vectors.
Yes.
Coordinate vector, yes, sir.
Yes. So 1 5 minus 2 means multiplying with 1 5 minus 2 will give you 2 plus 4 into 5 minus 2 into 5, then 3 into 1 minus 1 into 5 plus 2 into minus 2, 1 into 1 plus 5 into 3 minus 2 into minus 1. That is 20 minus 10. Twelve minus 6, 20. So that is the correct answer. That is the coordinate of that answer, but with respect to standard message, that will give you the same similar thing, just transpose. Is it clear?
Yes, sir.
Okay. So let us see the next question. So W is a finite dimensional inner product space and E is orthogonal projection of phi on W. Alpha beta belongs to phi, then which will be satisfied. Okay. So we need to observe some fact. First, uh, what projection satisfy a formula, right? What is that formula? So a projection is defined by E square equal to E.
Idempotent.
Idempotent. So orthogonal projection satisfy the same formula. Why? Because suppose okay.
Sir, operator is projection if and only if it is idempotent.
No, that is for projection, but for orthogonal projection, idempotent is not enough. Okay, it satisfies some additional conditions. So in this problem, I'll explain why any idempotent is not orthogonal transformation. Even that, yes. Okay, so let me explain this problem. So let W is, so we have W is EV, right? And we can write V as direct sum of W plus W part. Okay. Therefore, any vector V can be written as W V component of phi on W, so denoted by phi1, and component maybe phi W, PE. Okay, and another thing is EV plus I minus EV. So this is V. V can be written as this. So what is EV?
W.
EV is same as this.
W.
Yes. So maybe write it in a different notation. It will be more easy to explain. So V can be written as
EV plus I minus EV.
yes, V in the direction of the subspace W plus V component of V on W perf. Maybe W perf. So let W perf is denoted by some complement. So normal to this N. So V can be written as VW plus Vn, right? So if we apply VE on this V, then this will be the same VW.
That will be 0, sir.
Yes, E applied on Vn, that orthogonal complement will be 0. Now again, if we apply E square V, this is same as E applied on VW, but VW is already in W. That will be VW itself. From here, it is clear that E applied on V and E square E applied on V will give you the same thing. Therefore, E square equal to E. Is it clear?
Yes, sir.
Okay. Now, another important property. So, this is therefore E is idempotent. Another important property is E should be self-conjugate. That is self-adjoint. Sorry. Okay. So, another property is self-adjoint. How can we show that? So let me start with EV comma W. Maybe not W because W notation is already used. EV
Let's
comma
EZ.
yes.
You
Maybe
can take Y, sir. Y.
yes. Maybe we can write EV1 V2. Okay. Or EV V dash. EV V dash. This is, let us fix it. This
So we need to prove, sir, this is equal to V inner product V dash EV.
yeah. So any element V can be written as VW plus Vn. Similarly, any element V dash can be written as VW. Let this where VW belongs to W and Vn belongs to N. So similarly, V dash can be also written as V dash W plus Vn W, Vn dash, right? So if we use the first expansion, then we have VW plus Vn. What is EV? EV is same as VW, right? Which is same as VW dash, and V dash is same as VW dash plus Vn dash. Now this is same as VW or VW dash plus VW inner product with Vn dash.
First will be 0.
First one is non-zero because both we don't know. First one, both are in the same space.
Yes, sir. Yes, yes. Second one is 0.
Yeah. Here, first one is in W. Second one is in W perf, that is normal component. Therefore, the second one is 0 actually. So this is actually same as this is actually 0. This is same as VW, comma VWS. Now we do the opposite thing. So VW can be written as VW. So similarly, we can show that if we start with V, EV dash, we will get the same thing, right? For V, it is V plus Vn dash, V plus Vn, but EV dash means it is actually VE dash. My notation are not so good, that's why I am making lots of mistakes. So, sorry, VW. Okay. Now again VW, this inner product will survive, right? Therefore, EV comma W, EV comma V dash is same as V comma EV dash. This is true for all V comma V dash. But we also know EV comma V dash is same as V comma E star V dash, right? We also know this. Therefore, comparing what we have, what we'll get. Comparing, we get from those two things, we get V comma EV dash is same as V comma E star V dash, right? For all V dash, just right hand sides. Those are right hand sides. So V comma E V dash minus E star V dash equal to 0 for all V dash. So again, if you choose V equal to same as choose V equal to E V dash minus, sorry.
So this is only when true, na, sir. If EV dash minus E star V dash is 0.
Yes, that is true. Only the second component must be 0. Yes, I am proving that part. That is actually repetition. E minus E star of V.
Yes, sir. Norm is 0 only when the vector is 0.
Therefore, E minus E star V equal to 0. That is, EV is same as E star V. This is for all V. Therefore, E is same as E star. So, any orthogonal projection must be self-conjugate, self-adjoint. That is, adjoint operator of E star is same as E, which is not true for arbitrary projection. Okay. So now let us see which options are true. Maybe we can what can be done. Okay. It is so let us see which option. So we know that E is projection, orthogonal projection. This will imply I minus E is also orthogonal projection, right? This is orthogonal projection on W, then this is orthogonal projection on W perf.
Yes, sir.
So this is orthogonal projection. We know that any orthogonal projection is self-adjoint. Therefore, I minus E is self-adjoint.
Option A is not correct. Option B is correct.
Yes.
Option C is also correct because E cube is E simply. No, no,
Yes.
sir. Yes, sir. This is
So this
correct.
is correct. This is
C.
correct because self adjoint. This means actually. Let me write the all steps. I alpha this comma beta. This is same as alpha comma I minus e beta. A star I minus e star is same as I minus e. We have already proved. Let me denote it by 1 by 1. Self adjoint by 1. Now E alpha comma beta, this is also easy to see, right? E alpha comma eta is same as alpha comma E beta
So E
by
cube is simply E.
yes by 1, but E square is also E. Therefore, since E square is E, therefore E cube is also E. So this is alpha comma cube. So this option is also correct. And now, what about the last option?
This is also correct.
Okay, let us see.
So
So
we have to expand the second term, sir, by writing I alpha minus E alpha.
yes, alpha can be written as E alpha plus I minus E alpha. And this part belongs to W part and this part belongs to W. So if you just multiply the product, then cross terms E alpha inner product with I minus E beta, so those terms will be cancelled. Those are orthogonal. So this is also correct, right? Only these terms will survive. The cross term will get cancelled. Those are orthogonal. Now this is not true. You can check with any counter example. This is in general not true. So we also know that ortho you can directly write this is not true because why? Because we know that T star adjoint operator is also unique. So it is therefore since adjoint operator is unique, therefore I minus E and E those cannot be same. I minus E can never be same as E. This is not possible.
Yes, sir.
This is only possible when 2E is same as I, but 2E that means E equal to half I, but that is not orthogonal projection because that will not satisfy the property P squared equal to P. So this is not. Is it clear what is the problem? What is the issue?
Yes, sir. Because E is self-adjoint, so I minus E must be equal to E. But
Yes.
in that case, E should be I by 2, sir.
Yeah. That is not possible because E is orthogonal. Okay, so that was our last problem. Okay. Is there any doubt up to this?
No, sir.
Okay, if there is no doubt, let us stop.
Thank you, sir.
Welcome. So I am. Yeah.